Professor Buddy Ratner is our second distinguished lecturer today. Professor Ratner is a professor of chemistry, chemical engineering and bioengineering at the University of Washington. He got his PhD at Brooklyn Polytech some 37 years ago. Since then, he wrote many papers, 400 papers, and got many awards. One of them being the just recently received 2009 Biomaterials ACTA Gold Medal Award, which was delivered to him in Lausanne by the European Society of Biomaterials. He's currently the director of the NSF Engineering Research Center of the state of Washington. In 2002, he was elected member of National Academy of Engineering in the USA. And Professor Ratner will talk about tissue engineering biology, scaffolds, material science. Professor Ratner.
Good morning. It's really quite a great honor to be invited to give a plenary lecture, and that gives you a wonderful opportunity to expand upon a subject and hopefully to deliver some new ideas. And the title may be a little bit complicated, but the central theme is this subject, tissue engineering. I'll try and discuss its impact. But I think there's some very new ideas that are developing in tissue engineering that may totally revolutionize the field, and that revolution will have tremendous impact on the way we deal with, with medicine. So, do we have a pointer here? Is there a laser pointer, or maybe not? Okay, if not, so if we look at this slide and go towards the top, this idea of biology, scaffold, material science, the biology indicated by maybe a whole organ is quite a complicated. This button. Yeah. Okay. That's good. Thank you. Yeah. Okay, it doesn't seem to have the intensity. You can light my hand, but not the screen. Anyway, we'll just talk through them. That's okay. Yeah. Here comes another one. Yellow. Okay. Much better. Okay. Good. So we start with an organ, and the organ might be made from some cells. Maybe proteins, I think, would be appropriate. On the other end of the scale, the material science end, we deal with things of mechanics and materials, and we're going to try and work along and look at this continuum. So my central interest for these 37 years that I've been at the University of Washington have been in medical devices, and these are very, let's call them practical, worldly devices. I have some numbers, which are the number of humans per year that receive these devices. You can see the numbers are very large. I'm not going to elaborate on them, but what it does mean is that millions of people have their lives saved or the quality of their life improved by today's medical devices. And that's, I think, been a pretty good development that's happened since the 1950s when these devices first were envisioned. But with that platform, that's today, I'm making a prediction, and predictions are subject you to always some skepticism. People say that futurists are 100% wrong, but I'm going to try and make a prediction anyway that tissue engineering will revolutionize the field of medicine in just 10 years. And 10 years is really a remarkably short period of time to take a medicine platform that goes back so long and totally change it. So let's see why I believe this. So what I might call the roadmap for this talk, we'll again talk about tissue engineering, something about these ideas of scaffolds, type of scaffold that heals, some new polymers, put them into tissue engineering, and then bring this together on some new ideas on healing and regeneration. So let's start here with tissue engineering. This is from Business Week magazine right away. That tells you something of the perspective on this article. 1998, Business Week talks about replacing skin, bone, urinary tract, bladder, cartilage, spinal cord, nerves, liver. At the time this came out, this was totally hype. There was no reality to any of this except perhaps a little work in the area of skin that was just beginning to happen. But it was a very pleasant vision. And then we go to today, and you can find on the front page of the Washington Post, it's a 2006 date, the first bladders grown in the laboratory were transplanted. There's some 20 humans that have bladders that have been completely grown in the laboratory, now replacing what was a non-functional bladder. There was a 2008 article of a woman who had her trachea completely replaced with a laboratory-grown trachea. There are skin products on the market. Dermagraft is a skin let's call it a device to assist in the healing and reconstruction of skin that contains living fibroblast cells. So this is the reality today. It's quite a change from that 2000 or 1998 Business Week article that was all fiction. The central idea behind this tissue engineering revolution might be very simply described as seeding living cells into a porous scaffold. And I think, although there are a number of ways to do this thing we call tissue engineering, I believe this one, seeding cells, dominates the field. And these porous scaffolds have to serve a number of functions. This is, I think, the engineering philosophy behind them. If we look at a development going from just a bunch of cells, which are not so interesting, to a tissue or an organ over some time, and I have 1 month here as just a suggestion, we find that the cells, of course, under the right conditions, will grow with time. And as the cells grow, they make a mechanical matrix, so the mechanical strength, mechanical properties of the tissue will improve. As these cells grow, they have a demand for oxygen, and they will suffocate themselves if not provided. So we need this process called angiogenesis, blood vessel formation, to happen rather rapidly to introduce blood vessels there. We have another process called inflammation. Inflammation is the normal process of healing. It has to, inflammation, sometimes the word sounds like a problem, but actually it is defined in the medical textbooks as the normal process that we heal and regenerate. And inflammation has to increase, but then it has to go away. And then finally, the scaffold itself must degrade with time, and ideally the scaffold should be gone when we have our tissue. So that's really what we're aiming at. Here's part of the problem. It's illustrated here. This is a scanning electron micrograph. This Teflon device is actually a glucose sensor. And it was implanted in a rat for 6 weeks and then examined. And what was found was that this Teflon device was completely encapsulated by a dense collagenous capsule, a bag, totally surrounded it. This is more what normal tissue looks like over here. And so the consequence of this was that that Teflon device, the glucose sensor, would no longer function because the diffusion of glucose through this dense layer was severely inhibited. So this is the reaction, what you're seeing here, which we call the classic foreign body reaction. And if we examine this in maybe a cartoon form, what we find is that if this strange object here is our biomaterial or a medical device, At the earliest times when it's placed in the body, there's a layer of proteins that gloms down on the surface, adsorbs very rapidly to the surface. Time zero is relatively accurate. Within just a few seconds, there's plenty of protein on that surface. Sometime later, these cells called macrophages come down, and their function is to interrogate foreign objects that invade the body. When they see our biocompatible biomaterial, they're actually not all that pleased, even though it might be labeled by the regulatory agency biocompatible. They don't find this at all amusing. And they attempt to spread out, to engulf, and to eat this biomaterial that has invaded the body. When they find that our titanium materials and our silicone elastomers are indigestible, they eventually call in some other cells which put the capsule, and that's what we saw in the glucose sensor, around it and wall off the biomaterial. So that's the reaction we call the foreign body reaction. And an interesting thing, here's just another aspect of it. If this green thing in this case is our biomaterial, we can say that the present definition of biocompatibility would be the implant after approximately 1 month is found within a thin, relatively acellular, no cells, avascular, collagen bag, collagen sac. The reaction site is relatively quiescent. I think most physicians would say, this looks biocompatible. But the important point about this is it doesn't matter if that green thing is titanium or polyethylene or carbon or polylactic acid, polyethylene terephthalate, platinum, alumina. The body is, again, very non-discriminatory. This is a foreign object within the body space, and the body will put essentially indistinguishable wall around them all. Our material science is not very well respected in this context. Again, to bring this back to the issue in tissue engineering, if we in tissue engineering, what people have found is they have this scaffold seeded with cells. And what we do with this scaffold typically is put it into a bioreactor. And these cells, if they're in an environment they like, will produce a matrix, an extracellular matrix, a proteinaceous matrix around it. And then if we take this developed tissue engineering scaffold and implant it in the body, what we'll find that it actually integrates rather nicely. And blood vessels grow in, and we start to get an integration of tissue. This is the tissue engineering concept. On the other hand, if we took that exact same scaffold, our biomaterial scaffold, let's say, without cells, and implanted it, what we'd find is every fiber would be totally encapsulated in a scar. So the ability of these cells to produce their extracellular matrix within the scaffold allows it to heal. Now, where I'm going to be going in this talk is that I'm going to talk about a new type of scaffold. I'll introduce this a little later, that upon implantation becomes heavily infused with these cells I called the macrophage. I described them before. And this infusion then, upon implantation, leads to this vascularized tissue reconstruction. In other words, we have not had to precede this device with cells. We get this reconstruction anyway, and that's where I'm going, and I'll work my way to that. So there are many ways to do these scaffolds, to make these scaffolds. Again, the materials science community has been remarkably fertile in coming up with a whole list of methods, and I don't have nearly the time to go through this. But what I am going to do is focus on two of them. One of them will set an example. It's called an Afron. Then I'm going to talk about a technology called microsphere templating. And so let's look at these Afrons. Afrons or the term comes actually from the chemical engineering literature, and what they really are, I sometimes think of them as a very fancy cappuccino. It's a ultrafine foam. Typically, one uses a stirrer with a specially designed baffle that distributes the shear force within the liquid and gives a very nice foaming. And again, in this example here, we have our stirrer and our baffles, and we're going to. I'm not going to go into the details of the scaffold. The scaffolds I'll show you, the Afrons I'll show you. But we're going to make some foam, we're going to freeze it and lyophilize it, freeze dry it, and maybe conjugate some other things and make a scaffold out of it. This is what it looks like at the beginning, and then we foam it up, and indeed we get a large amount of foam. You can imagine if you ever want to make a very large quantity of tissue engineering scaffold at a very low cost, it's going to be a very good technology. And then one looks at these aphrons, and you see we get some very interesting foam structures. The scanning electron micrographs are a little dark, but these are interconnected structures. They are not closed cell foams, and we've explored these with some tissue engineering applications. So these are nice, they're very easy, but here's one of the problems that was kind of disturbing us about these. Is if you look at them closely, this is another one made from a polymer called an alginate, really made from seaweed. It's a saccharide made from seaweed, that is. And if you examine these scaffolds, what you find is they'll typically have quite a distribution of pore sizes, large pores, small pores, medium-sized pores. So we want to look at these porous materials in healing and regeneration. If we ask the question, what would be the ideal pore size, we'd be pretty hard-pressed to tell for materials like this. So we did a literature review. We found people going back at least into the 1970s were implanting porous materials and looking at healing responses and seeing some interesting things happening. But you go through the complete literature, and this is just a few representative examples. There are hundreds of papers on this subject. They all have these materials that have this broad distribution of pore sizes. So again, we could not come up with the question of what is the ideal pore size. So we decided to address that. And so what we did was develop a technology that was borrowed from some other methods, templating methods, but applied to tissue engineering. And so we took some microspheres, these are in the micron range, and we sieved them to get very fine cuts. And then we ultrasonicated them so they settled down into a tight-packed array, close-packed array. And then we gently heated them so they sintered or fused into a mass. And then we surrounded them with a monomer liquid. Then we solidified or polymerized that monomer liquid. And finally, we used the solvent to extract out the spheres. So what we're left with is an interconnected structure, interconnected where the spheres were sintered together, an interconnected structure where every pore is the exact same size, and that was kind of what we wanted. So this is what the spheres look like when they're shook down and sintered, and this is what the material looks like. And so this is a cut through a material, and these black dots are the places where the spheres were sintered together. And this shows a large piece of it, so you can see the uniformity of this pore structure across a big chunk of it, the type we might use in an implant. And the results were very striking. If the pore size was just right, and just right turns out to be around 35 microns, this is blood vessel density. And blood vessels are a sign of a regenerative, reconstructive healing versus that collagenous scar. So if the pore size was just right, we got a very profound level of blood vessels produced in here. If the pore size was up around 160 microns, there was hardly any blood vessels. And most tissue engineering scaffolds are up around this size. If we looked at the solid material, I don't have it on here, but it looked almost identical to the 160 microns. So there's a very sharp maximum. You can see with error bars here. And one of the interesting things in this healing response, this is a stain, a biological stain for these cells called the macrophages. It's specific to the macrophage cell, and the more brown, the more macrophages. In the 35 micron material, this is richly populated with these macrophage cells. Remember, all these materials, these are close-packed spheres, so they all have the same void volume, roughly 70% void volume, and yet just the 35 micron is densely packed with these macrophage cells. If we look at this collagen capsule, the foreign body capsule, we find there's a minimum at 35 microns. in the healing. And interestingly, although I don't have the data here, we do have the data that we sometimes present, but the capsules are comprised of less dense collagen. So as well as being the capsule being thinner, this is actually a rather open, diffuse collagen rather than a dense bag. And we started exploring these. Our Department of Dermatology and the University Hospital got quite interested in this class of materials. They've been working for years to try and get a material that can go through the skin. It would be useful for catheters and electrodes, a variety of needs. And the problem with present implants that go through the skin is that they never heal to the skin. And so bugs, bacteria, infection can crawl right down, and infection is the classic problem. But also the outer layer of the skin, the epidermis, literally tries to grow around the device and extrude it to push it out. It does not like things through the skin. So they started working with our sphere templated material, and Dr. Olerud and his group developed a model where this red is a rod of this sphere templated material, put it through the back of the animals. You can see what it looks like here. And the results were quite striking. So this rod of material went through the animal just like this. And so you could look at the healing of the epidermis, the outer skin layer, and the dermis, the inner layer. And there was a lot of data here that came out of this particular study. What they found, this is a specific stain for the epidermis. It grew right through the material, sealed off the material, and then you start looking in the inner space within the material, in the dermis, and you find new blood vessels are recreated, fibroblast cells. You find a reconstruction of the dermis. So both the epidermis and the dermis, the skin reconstructed itself right through this material. I don't think that has ever been seen in medicine. And interestingly, this healing response was seen with a silicone elastomer, with a hydrogel. We immobilized collagen and a lamin into these. It made no difference. We got the exact same healing response with silicone, hydrogel, with or without collagen or laminin. So it was controlled by the pore size, not the nature of the material. This was exciting enough development, so a company was spun out of the University of Washington. It's called Helionics. And they call the material STAR, which is sphere templated angiogenic regenerative material. They've optimized some of the manufacturing, and they get an extremely uniform type material now that is being sold. The first product is on the market, which is a scleral implant. Goes through the white of the eye, if you will, but at the moment it's aimed at the veterinary market. It's a glaucoma drain for dogs. And the company that was making these originally never saw more than 3 months of success or use of this particular glaucoma drain to relieve the eye pressure in animals. When they started using this material, they're up to well past 2 years in a number of animals, and it's performing very nicely. So it shows this healing in this very difficult environment, the sclera of the eye. And in fact, in a project, Dr. Shai Garti and Dr. Tung Shen in our Department of Ophthalmology and Bioengineering and myself have been making a corneal replacement that also would have a ring, a skirt of this porous polymer, sphere templated polymer, to heal in, and an optical zone in the center. And the initial healing results show a very intense integration of living cells just growing in and out and through this material rather than just scarring it off. And so we're very excited about this development. And again, this is quite a difficult environment to get healing in. One of the professors in our Department of Orthopedic Surgery heard about this too, and he has an animal model to explore materials for bone healing. He likes old rabbits, because old rabbits don't heal their bones very well or heal very slowly. And so this is Dr. Paul Manner's work. And when he implanted this sphere templated polymer into bone, this is what the original bone looks like, and what he found was new bone just growing into this sphere-templated structure. This is the control, which was just a divot, a hole drilled in the bone and allowed to fill with clot. And basically, there's nothing there. There's no reconstruction, essentially no reconstruction at all. We used the micro-CT method to examine the mineralization. And here's the cut in the control. Here's the cut where the scaffold was put in. Unfortunately, this is the contralateral side, the control, and they kind of got reversed. So this one and this one are the two controls. Here's just the divot that was drilled with no scaffold. Here's with the scaffold. And if you examine the data here, this is % bone regrowth. And there are two experiments. It's a dark blue bar and a light blue bar. And so here's the just the amount of bone regrowth in the empty divot, and then filled with the scaffold. You know, it's got a tremendous amount of bone growth. Empty, filled, tremendous amount. Here's empty, filled. This dark blue one didn't do that well, but clearly most of them regrew the bone very nicely, enthusiastically. And if you examine them, this is the sphere templated material, and you can see some fibrocartilage on the surface of the knee with no scaffold. There was just some clot and scar. It looked pretty ugly there. So this was actually a pretty unexpected result, the whole thing, that the material we're using was basically the material was soft contact lens, and you wouldn't expect that to heal in bone. We didn't use this cytokine BMP2 that many people are using to stimulate bone growth. We didn't use any calcium phosphate mineral phases to stimulate the growth. We used no stem cells, no osteoblasts. And almost everybody in the bone field feels you need pores greater than 200 microns, and we use 35 micron pores. So this kind of defied almost every conventional wisdom in bone healing, and yet again talks to the regenerative capacity of this type of material. So what's going on here? Why does it work? Well, we believe the macrophage is the key element that controls this cell critical to normal healing, long-lived at the implant surface. It can synthesize most cytokines. And we believe the macrophage knows what components to make and when to make it. It knows how to orchestrate healing. That's its function. And we're just taming or controlling the macrophage to achieve this healing. And the way we're doing this is kind of interesting. Again, this is hypothesis, although we have actually the first bit of evidence that is strongly suggestive of this right now. And so on the non-porous material, this macrophage comes along, again, attempts to phagocytose or engulf the material, eat it up as foreign. In large pore materials, the macrophage has plenty of room to spread out, again, going to this futile attempt to engulf or eat the material. But in these small pores, the pores are big enough for the macrophage to go in, but not big enough for it to spread. What we believe is happening is the macrophage is being mechanically constrained, and so it's the biomechanics that's really dominating the healing process, and not a specific biorecognition clue or proteinaceous clue. And we'll get back to that point, too. The field of macrophage biology has undergone a bit of a revolution in recent years. We used to just talk about one cell called a macrophage. Now people are finding there are many different types of macrophages. And so this paper describes an M1 and an M2 macrophage. And the M1 macrophage is responsible for killing of parasites, for tissue destruction. The M2 macrophage is responsible for angiogenesis and tissue remodeling. Well, that sounds a lot like we're doing. So are we getting M2 macrophages? Well, the initial results, actually the data isn't down here, but the results are in, and the initial results, this just shows our ability to stain the macrophages in the different phenotypes. But the results are in, and it shows that, in fact, within these sphere-templated materials, there's an enrichment of this M2 phenotype that leads to healing and reconstruction. There's other people that have seen this type of healing and reconstruction by completely different ways. There's a type of material that was invented by a man named Steve Badilak. It's called a small intestinal submucosa. It's taken from the submucosa of the pig. Cells are removed, decellularized, and so here's what maybe the pig extracellular matrix looks like with cells. And what happens is we've decellularized it and taken the cells out and left just the extracellular matrix behind. And this particular type of material has gone into millions of human surgeries, and it seems to heal, again, with a lot of macrophages, a lot of angiogenesis, and a very regenerative type of healing, much like we're seeing with our synthetic materials. So Dr. Badylak has felt there are 3 criteria necessary for this type of healing, this reconstructive, regenerative healing: abundant angiogenesis, abundant mononuclear cells, and rapid epithelialization. And what do we see with our porous sphere-templated polymers? We see abundant angiogenesis, abundant mononuclear cells, and rapid epithelialization. So it seems like we're both going down a similar path. And so I think through much of history, what we might call the default mechanism of healing was scar, maybe a mechanism to quickly cure us from beasts like this and ensure we can pass our genetic material to the next generation. But we now have a change. We no longer have this particular default mechanism of healing. We have kind of a revolution in healing that can lead to normal extracellular matrix, to angiogenesis, to reconstruction. And these materials, the 6S, or sphere-templated materials, seem to give it. This decellularized tissue gives it. People are doing this with extracellular matrix, cytokine triggering, the tissue engineering ideas. My hypothesis is in all cases we're taming the cell, the macrophage, and it does the reconstruction and the regeneration for us. Just to go back to Dr. Badylak's material, this material, you'll notice the pore structure here looks nothing like our highly organized pore structure, but we believe it works by a completely different mechanism. Both materials are heavily invaded by these macrophage cells, but in the case of Dr. Badylak's material, the cells, the macrophages, since this is biological, the macrophages degrade it to low molecular weight peptides, and we believe these peptides actually are recognized by the macrophage that lead to the healing. In our case, the macrophages are inhibited from spreading, and that drives the macrophage into this phenotype. So that's hypothesis about what may be going on here. And in fact, Dr. Badylak published a recent article showing the effect, the strong biological activity of the degradation products of this material. So just to, again, recapitulate some ideas, the pHEMA porous material heals in with this regenerative angiogenesis. The exact same material in a solid form just gives a scar. Interestingly, the regulatory agencies, the FDA in the United States, for example, would call both materials biocompatible. But look at the difference in the reaction, kind of a night and day difference in reaction. How can we call both materials biocompatible? So I think this is going to lead to a redefinition of that term that's very widely used, but I think this may give us more specificity in the way we use that biocompatible term. Okay. We're going to take this eventually and talk about these sphere-templated materials in heart muscle tissue engineering, but I just want to take another short diversion and talk about some new polymers for tissue engineering, and I'll talk about a biodegradable pHEMA and polynipam polymer. So most of the results you saw, the data on that sphere-templated material, was based upon this material that is the material of the soft contact lens. It's called pHEMA, hydroxyethyl methacrylate. It's been used in medicine since 1960, and it is remarkably biostable. But there are 2 facts that we do know about this. One is that if we take this material in an uncross-linked form, it's simply not soluble in aqueous. And another fact is that the HEMA monomer itself, the low molecular unit, is soluble in aqueous. So that makes us think that someplace between the monomer and the polymer, there might be some level of degree of polymerization that is soluble. And in fact, that is the case. So the rationale for these new polymers is to keep the HEMA chains less than 6,000 Daltons and then cross-link them with a biodegradable crosslinker. And so we developed a crosslinker that has some polyester units, polycaprolactone units, breaks down into caproic acid, which is part of the normal metabolism. And this just talks about some of the organic chemistry that went into that. But the general idea is, if we just took the HEMA chains and cross-linked them, if the red is these degradable crosslinker units, and they degrade, we'll still have these long, non-degradable, non-water soluble, high molecular weight HEMA chains that the body really can't clear or degrade. So the idea is to put backbone linkages too, and then when the whole thing breaks down, it's in little fragments. The short fragments can be soluble and can be cleared through the kidney. So we used a new method in polymerization, a relatively new, called the atomic transfer radical polymerization, ATRP, which gives us very precise control of the molecular weight and molecular weight distribution of units. And so we can put in now little 5K segments of HEMA cross-linked by this degradable crosslinker. And this talks about the particular initiator we're using, and this is the crosslinker I showed you before. The problem with that, we made that polymer. It had, it certainly degraded appropriately, but had very poor mechanical properties. The 5,000 molecular weight units was simply too, not quite macromolecular enough to give macromolecular type properties. So one of my PhD students, Sarah Atzett, developed a polycaprolactone that has these ATRP initiators at the end and allows her to initiate HEMA chains off a degradable segment. So now we have in the backbone a polycaprolactone unit and crosslinks. And you can kind of see that again, the kind of pinkish color is the crosslinks, and then we have these backbone units also polycaprolactone. And we can engineer these crosslinks to put in various types of esters. There's a few different: polycaprolactone, polylactic, polyglycolic acid. It gives us a lot of flexibility. We can use the polyethylene glycol to increase the hydrophilicity. And so this gives us a lot of engineering options for designing this. And so we're going to ask, are these going to degrade? And we can look at three things. If we're breaking crosslinks, we'd expect this to swell more. The swelling should increase. If we're breaking crosslinks, we expect the mechanical strength to go down. The tensile modulus should go down. And if we're breaking crosslinks, it should lose mass. So, for example, we can look at, in this case, the swelling ratio, and we're using a lipase, an esterase, to speed up the degradation. But sure enough, this is the blue ones are a biostable one. The red ones are the degradable ones. And sure enough, the higher the concentration of lipase, the more rapid the swelling. In other words, we're breaking down those bonds. Similarly, we can look at the tensile modulus and notice the tensile modulus decreases with size in a dose-dependent fashion with the amount of lipase. And we could also look at the mass loss, and again, see the mass loss increasing with time on these materials. Again, this is the non-biodegradable one, and basically has no change over time. So what's going on here? Well, this is the process we think is happening. We have our cross-linked material, and at first we start breaking cross-links and it swells. And then we start breaking backbone units and we start solubilizing pieces out of it. So we think that's the mechanism that's happening. And this is a section of this material that is on the stage of a confocal microscope. We're just going to add some strong KOH to rapidly degrade it. Let's see if the movie's going to work here. Yeah. So add the KOH, and basically, although actually the movie didn't complete itself, the whole thing goes away. And, let's see, I'm not sure why it didn't do that. Anyway, the whole thing does completely dissolve off the stage of the microscope. We can kind of watch the degradation process, this swelling and then dissolution. Another question is, what about these fragments? Are they toxic? Well, this is an assay for toxicity. And basically, we're using an enzymatic process to make a color change. If the cells are alive, they have this enzyme and they make this color change. So you see this nice color absorbance. Latex is pretty toxic to cells, and we don't get this color change. So this is the control, which is a tissue culture polystyrene. The cells make plenty of color, and various doses of the degradation product from this have essentially no effect on the cells, so it is not toxic. We've been optimizing this even more. Dr. Anna Galperin has been developing some very nice chemistry using this particular unit that's called methylene dioxapane in the polymerization. Are we getting near the end? Okay. Yeah. So try and finish up here quickly. Using this unit to make some very nice backbone units of these degradable units. And now finally we can get to the tissue engineering. We have a project which is actually intended to put new heart cells into damaged heart tissue. And skip a lot of the details here. So what we're trying to do is recapitulate what actual heart tissue looks like with muscle bundles and many blood vessels near the muscle bundles. It's pretty demanding to actually remake a tissue of that complexity. So we have a program, NIH-funded program called BEAT, which has 8 teams, each addressing a different aspect. And here's the many professors and researchers that are heading each of these teams: scaffolds, mechanics, cells, surgery, gene delivery, angiogenesis, extracellular matrix, electrical properties. We're addressing all these things to try and put this all together. And the challenges are cells, but we also have a challenge of blood vessels, to bring blood vessels into these materials. The cells have been somewhat simplified since we have a new president in the United States. Our old president made it very difficult to use the best cell lines, and now that obstacle, I think, is out of the way. And what we're trying to do is implant these, what we call rods of cardiac muscle, right into the wall of the heart. Just shows an example of maybe the dimensions of these rods. They heal into this sphere templated scaffold heals beautifully into the heart. I'm not going to go into the detail for lack of time, but it heals very nicely into the heart, which is very subject to scarring, so that's quite interesting. And we can put these cardiomyocyte cells into the sphere templated material. They stay alive. We are trying to align the cells because the cardiac cells have to be aligned. We've developed another templating process using optical fibers, actually, to develop a material with long channels for cells and the sphere templated structure for angiogenesis. And this just compares that material to heart muscle. And let's see here. Let's skip this again for lack of time. And then we're seeding cells in, and we found that these cells populate the heart cells, populate these long channels. You can see them in the long channels. And then we implanted it to heart muscle. What we expected to get in these long channels was heart muscle through them and angiogenesis throughout. This is the histology, which I'm not going to go into for the sake of time, but actually what we found was down these long channels, the body put large blood vessels, which were then surrounded by these cardiomyocyte cells. It's a bit of a different reaction from the one we expected, but actually potentially a very good healing reaction. So we're studying this further. There's just more data on that. And anyway, let me just finish up. These sphere templated materials have shown excellent healing in a very wide range of very different body sites: bone, sclera, heart, skin. Independent of polymer use, kind of a new paradigm in healing. We're wondering if actually this macrophage cell maybe differentiates into the other cells. People would say a macrophage can't differentiate, but we have some indirect evidence that, in fact, it does. This talks about some of that evidence. But then people are publishing papers, macrophage characteristics of stem cells. Could the macrophage be a stem-like cell? And then also people have recently published, November 2009, that this macrophage can self-renew. People didn't think the cell could multiply, but people have shown under the right conditions it can. So what we have here is, I think there's a change in the wind. The micromechanics may be important. There's sort of a new paradigm in healing. The default mechanism of healing, scar, can be replaced with a vascularized reconstruction. And we may see a redefinition of the word biocompatibility as we go from kind of a dead idea to a real vital living idea. And so with that, let me thank many students, investigators, and staff who have been involved with this, the NSF and the NIH for funding, and I appreciate your attention and listening to this talk.
Thank you. I'll take one question, and we'll have to leave the remaining questions for the coffee break. So one question, if there is any. Yes.
A very exciting talk. I have one question. You show that these microspheres, when chosen to be 35 microns, work better than the 200 micron size spheres. Now, did you ever try some polydisperse distribution to check several different exact polydisperse distributions to see which one works better? Because in biology, usually you have polydispersed things, or in many cases you do. So maybe if you add smaller pores to the 35 microns, you can do even better than that.
Well, you know, if you have big pores mixed in, these macrophages seem to go into the spreading mode, and we get more scar. So again, it's quite optimized at the moment. It's a very tight range. We call it the sweet spot between 30 and 40 microns. And you know, when we use polydispersed materials, we just don't get this same reaction. It's a very tight little zone that gives this excellent healing response.
But can't you go to smaller pores to add in smaller pores?
Well, the problem with the smaller pores is the macrophages just can't fit in anymore. They can't make it deeply into the material. The 35 micron allows them to get in, but doesn't allow them to spread, and we think that's the secret.
Okay, thank you very much. I'd like to thank both speakers for a great session.